This conference will now be recorded.
Okay, so good morning all and welcome back to the session that is Big Data Masters program, and we are going through with distributed processing with PySpark. Yesterday what we have discussed about Spark SQL, and that is nothing but a library, or you can say a SQL API onto top of a Spark core that will provide us the benefit in order to write down the SQL like query for processing our data. And we have gone through with certain, you can say, operations like it is possible just by creating a temporary view onto top of data frame. We are going to read data frames with standard data read API, and writing is also the same stuff, like we are going to leverage standard data write API for writing the data, but for processing perspective we are going to leverage Spark SQL or SQL like queries to process the data that we have seen. And we have gone through with certain examples, like we were having small flights data and planes information, and based upon that we have joined that particular you can say tables, and because like we have created views onto top of data frames, and that data frame is acting as a table. And we have tried to perform certain, you can say, aggregation operations as well, like this particular data, two data frames was there, that is employee data and job title. So on to employee data and job title we try to do the aggregation and joining, like average is based upon the department, and like we try to fetch the job title of certain employees. So that we have done with respect to Spark SQL. Today I'm going to share an assignment with you all, and you need to work on to that particular assignment on in weekdays, in coming weekdays, and that will give you more insight about the Spark SQL related stuff. Then we have started the next topic, that was repartition and coalesce. So repartition and coalesce is nothing but the optimization technique in PySpark. So what is the meaning of repartition and coalesce? Say once we are having certain data, so based upon the data and the cluster availability, we need to increase and decrease the number of partition. Why so? Because we want to leverage the benefit of cluster computing. Second, if the data is reduced, then we need to say reduce the number of partitions, so that like small data will not be scattered throughout the cluster. You know, Spark is not going to provide good outcome with small files. This is an interview question as well, like why Spark is not providing a good outcome with small files. So small files create small partitions. Small partition will be scattered throughout the cluster, and like monitoring will be taking too much time at that moment. And because of that monitoring related stuff or control in information related stuff, it is taking too much time, and you will be having, you can say, highly unperformant job. So that is there with respect to repartition and coalesce. Uh, we, based upon the requirement and the cluster availability, we are going to increase and decrease the number of partition. And what we have seen, repartition is utilized in order to increase the number of partition, wherever coalesce is required in order to decrease the number of partition, because it is preferring local aggregation. Local aggregation means uh, data locality principle, you can say, like it is like trying to minimize the amount of shuffling, it working onto the data locality principle. So that was with respect to coalesce, and we have seen certain examples like increasing the number of partitions, and we have seen certain parameters like get num partition, default partition, and default parallelism. So default get num partition, min partitions, and default parallelism. So certain other parameters are there which are there with respect to partition, or you can say parallelism related stuff. And this repartition and coalesce can override those particular parameters. Then we have started another topic, that was cache and persist. So with respect to cache and persist, that is also an optimization technique. And what we have seen with respect to cache and persist, like say if we are having certain operations that we need to perform onto top of data frame or already, then after certain operations, like we are having say some refined data, and onto that particular refined data we need to write down a lot of queries. So in order to, you can say, avoid the execution of all the steps again and again, we are going to cache the outcome of a particular query which is utilized heavily. So what is happening over here, the data frame, the result will be stored inside the memory or disk, and as and when required, the result will be fetched, and the execution will be done, the query will be executed, huh? So these particular steps are not executed or avoided. And why it is happening? Because Spark is lazy in nature. It is lazily evaluated. Until unless we are not taking any action, nothing is performed. And once an action is there, then it is going to do the execution starting from the beginning. So that was there with respect to cache and persist. Like in order to avoid the execution of the steps again and again, we are going to cache a particular data frame. So that is possible. And how we can do that is very simple, like cache, like it is going to store the data frame inside the memory. And persist is going to store in memory or disk or in both of them, huh? So there are certain storage level inside persist, like memory only, memory and disk only, 2 3, okay, hop heap, and serialization, deserialization. We have gone through with these particular aspects, and how to implement persistence, how to persist the data frame, just like df.persist, and then you just need to mention the storage level. And that is possible, and we have gone through with this, and we have seen it with practically as well. And once you have done the operation on to top of the data, then don't forget to unpersist that particular data frame, because it is going to occupy certain memory inside inside or it is going to occupy certain space in disk or memory. So until unless we are not clearing, it will be, you can say, reserved over there. And for the subsequent applications, like another applications, it can create issue in sense like those particular application will not get enough memory. Okay, so that's why like we need to unpersist it, and if you are not like unpersisting, you will be facing a particular error, like temporary memory related issues will be there, so unpersist, we need to do the unpersist as well. So this was the stuff, friends, what we have covered in our previous session. Now, today we are going to focus on to the hardware related stuff, huh? So, say whatever we have discussed, like say partition, bucket, that is partition by basically, partition by, bucket by. Okay, we have gone through with these clauses, bucket by. Then instead of group by key, you need to utilize reduce by key. Say use reduce by key, reduce by key instead of group by key, group by key, and joining. Okay, and what I can say, this cache and persist, cache and persist, and avoiding collect. Okay. So these are nothing but optimization based upon the code level. So we are going to apply these particular things onto the code, and we will be able to do the optimization onto top of our data, or our application will be more performant if we guys are going to utilize these particular things. That is fine, but is there any other type of optimization that I can do? Okay, so if we talk about optimization in the PySpark or Spark world, there are two types of optimization: application level optimization, and resource level optimization, or cluster resource level optimization. Let me mention resource level optimization only. Resource level optimization. Okay, so whatever we have discussed so far, that is nothing but application level optimizations. Like by changing, by applying these particular, you can say, properties inside the code, we will be able to make our queries more performant. So collect, avoid collect, that is nothing but like once we are going to utilize collect, then it is going to fetch all the data towards the driver program. And if something is there towards the driver, then like it is going to provide out of memory related errors, OOM. So collect, we need to avoid. We know like reduce by key is working onto the local aggregation, and group by key is like nothing it is doing. It is going to perform the it is like moving the entire data, and then aggregation will be happen over there. So that is nothing but, let me give you certain insight about reduce by key and group by key and avoid collect, because we have used these particular things and seen these particular things practically. But let me show you what is happening once you are going to leverage reduce by key, and what is happening once you are going to utilize group by key. So say reduce by key and group by key, what is happening? And once we are having reduce by key, say I'm having reduce by key, say I'm having certain data. Okay, like I'm going through with frequency count program. I want to calculate the frequencies of words, and say I'm having three executors, say E1 and E2, E2 and E3. These are the three executors, and say I'm having certain data like big data, then big, and say booster analytics. Okay, so say these are the words which we are having in E1 executor 1. In the same fashion, certain words are there, say onto the executor 2, and certain words are there onto the executor 3. Okay, we are talking about reduce by key, big data, say big, say say big, okay, and say data. Okay, so this is like the data what I'm having into three executors. Once I'm going to apply reduce by key, so what it will do, and I want to do the aggregation. Aggregation, like I want to get the frequency of each and every word, like how many big are there, how many data are there, how many booster analytics are there. So once I'm going to utilize reduce by key, so it is going to perform the local aggregation. So once it is performing local aggregation, say big 2 is there, and data 1 is there, and booster analytics 1 is there. So this is with respect to say executor 1. Now with respect to executor 2, big 2 and data 1 is there, data 1. And with respect to executor 3, so big 1, 2, 3, 4, big 4 is there and data 2 is there. So now this particular result is being transferred from the local aggregation. So over here it is going to do the aggregation onto top of the data that it is having and do the aggregation. What I'm saying, local aggregation is performed over here. Say local aggregation is performed in over here or in this reduce by key, and the result is transferred, and intermediate result is transferred. Okay, so that is happening with respect to reduce by key. And once like another machine, it is given to the say another machine, and all that this particular data will be given to another machine, and over there aggregation will happen, and I will be able to get the final outcome. So that is there with respect to reduce by key. Now, what is happening inside the group by key? Once I'm applying the group by key, so group by key, group by key. Okay, so local aggregation will not be performed. Be performed over here. Okay, so once we are talking about this group by key, nothing local aggregation will not be performed, and it is going to, you can say, transfer this particular entire data. We are taking the simple example. Now previously we were moving the intermediate result. At this moment we are moving the entire data, and this particular entire data will be given to one node or one machine, and then over there the aggregation will happen and we will be able to get the final output. So this is not having say with respect to the processing of the data, it is not leveraging parallel processing. It is going to, you can say, transfer the data from all the machines. Say you can think in this particular way. Let me show you a diagram. Reduce by key and group by key in a Spark. Okay, so just have a look over here. I'm just opening this particular sheet. Okay, so over here, what is happening once we are using the reduce by key? It is going to say calculate locally and move the result. Say A1 B1 is transferred over here, A1 A1, so A2 is there. The count of A is 2, count of B is 2. Over here the count of A is 3 and B is 3. So this particular result is transferred. And now say A is give, we are having say two reducer. Just try to correlate with map and reduce. These are the mappers and this is the reducer. And same thing like executors, and like another executor which is taking say intermediate result, and it is going to perform the operation onto top of that. So a1 a2 a3, a1 from here, a2 from here, and a3 from here, a6 is there. So result is moved over here. And just have a look onto the group by key. It is nothing it is doing, it is going to say transfer the entire data. Say a1 is there, a1 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 is there, a1 a1 a1, so a1 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 is moved, and same is happening with b1. So over here it is not performing the local aggregation, it is going to move the entire data. So that is happening in say reduce by key. So these are nothing but application level optimization, and by you can say leveraging say reduce by key, we can avoid uh, heavy shuffling. If like we are using group by key, so a lot of shuffling of records will be there. Previously, say in case of reduce by key, we were moving the result, intermediate result, but over here entire data is moved from one machine to another machine, and because of this like it is having a lot of shuffling. So it is suffered from heavy shuffling, shuffling of records. And like shuffling is a critical operation with respect to big data world. And if shuffling is there, then it is going to degrade the performance. So we need to avoid this group by key, execution of group by key. And reduce by key is giving certain amount of optimization. And what is happening with respect to collect? So collect is collect what it is doing. Say once you are going to use collect operation onto top of a particular data, then what is happening? Say we are having these particular executors. Okay, executor 1, executor 2, and executor 3, and these executors are having certain data. Now say you have performed certain query, and you can take this particular example, say reduce by key you have performed, and uh, and then you have collected the data. So this particular data, the entire data, it is going to move towards the driver program. So once like a lot of data, say this reduce by key data is there, based upon the reduce by key operation, say data is there, say 5 TB data is there. Just taken an example, say three machines were working, were having certain data, and once they have processed, you have collected the data collected. Once you are going to execute the collect function or method, so what it is going to perform, it is going to move the entire data to the driver program, driver machine basically. So once like all of the machines are transferring the data to the driver machine, then that is going to overload the driver. Normally like we guys are going to provide less resources to the driver, because like driver is not performing the actual execution is performed by the worker nodes. So maximum resources we are providing to the worker nodes only. And even like say if the worker node is having say 24 GB of the memory, for the driver we guys are going to provide say 2 GB 4 GB memory. Okay, so once like say we are having thousands node cluster, and we have collected we have done the we have applied the collect operation, and at that moment what will happen, all the thousand node will transfer the data based upon the query that you have executed. It is going to transfer the data towards the driver machine, and the driver machine will go in OOM error, or out of memory basically. It will you can say throw out of memory error. So we should avoid this particular collect. We will see these particular things will with practical as well, but at this moment just try to build your concept like what is happening once you are going to leverage collect. Okay, the for the learning perspective, like it is fine say to collect the result, but once you are dealing with huge data, at that moment collect function is not preferred. You must avoid collect in your code. Okay, and what is the alternate with respect to collect? So the collect is save as text file. Basically, like you can write the output onto the disk, onto database or data lake, and if required, you can like query onto that particular data and provide the result to the customer or client. So that is with respect to collect. Now, what we have seen, say these particular things like partition by, bucket by, reduce by key, usage and joining, okay, usage of cache and persist, avoiding collect, and uh, these are nothing but application level optimization, like by changing certain things or by applying certain clause inside the code, we will be able to leverage these particular things and we will be able to do the optimization of our code. But what is happening with respect to the resource level optimization? Over here, the first thing that will come in our mind, like the resource, is the resource enough for the execution of an application? Okay, so you just try to recall that particular concept, that particular diagram, like where, like a client is coming. Let me show you. Okay, so where a client is coming and it is going to the resource manager, that is nothing but Jan, say, and it is asking Jan like, hey, resource manager, I want to do the execution of a particular job. Then this particular yarn manager is going to initiate an application master, and that is nothing but it is going to reserve certain containers on one node manager, and that container is nothing but the combination of memory and core. Okay, so over that particular application master is then going to bargain with resource manager, like for the execution of this particular job I just need to have the 2 executor or 3 executor or 10 executor, huh? So bargaining, post bargaining, the resource manager is going to provide those particular resources to the application master, and the resource manager job is over. Then application master will start uh, monitoring for those particular application, and once the execution is done, it is going to inform the driver, and then driver is going to inform to the client. So that is happening with respect to the execution of a particular job. But these particular resources, try to focus over here, these particular resources that you have given to an application, okay, is the resource. Executors are nothing but the resource, are those particular resources are enough in order to have the execution of a particular application. Okay, so that's what we need to think, that we need to learn over here with respect to resource level optimization. Over here we will be talking about the resources, so once we are having say resources, so resources is nothing but like the container, container. And once we say a container, that is nothing but a combination of memory and core, okay, memory, that is RAM, and core is nothing but CPU. So memory and core is nothing but a container, so let me take an example. Say I'm having 5 node cluster, and the cluster configuration is say 16 core CPU, and say 64 GB of RAM in each machine configuration. Each machine configuration is 16 core CPU and 64 GB of RAM. So what will be the cluster configuration, cluster uh, capacity basically, cluster capacity, 80 core and and uh, 640 into 5, 320, huh? Right? 320, is it?
Yes, sir.
Okay. So 320 GB of RAM. So like say I'm having a 5 node cluster, and the cluster, inside the cluster, like I'm having 16 core CPU, I'm having 5 machines and 5 worker node, huh? So 5 machines, so 16 into 5, so 80 core CPU, 80 cores, and 64 into 5, that is 320 GB of RAM. This is the cluster capacity. And each machine configuration, as I'm having 5, you can say node cluster, so 16 into 5, 80, and 64 into 5, that is 320. This is the cluster, you can say, capacity. Now, what I need to do, I need to divide these particular, you can say, this, I need to divide this particular capacity, and I need to like have executor from this particular capacity. What I can say, executor, executor are nothing but containers, huh? Containers. And what are containers? The combination of memory and core, huh? Combination of memory and core. So memory and core. So say, what will be the minimum, what is the minimum number, what are the minimum number of cores or memory that an executor can have? So an executor must have at least one CPU. Okay, one core basically. Yeah. So this is the bare minimum capacity for a particular executor, and that is saying, say, it must have at least one core. Okay, now based upon the available resources, I need to decide that how many executors are possible from this particular cluster configuration. How many executors? This is the cluster configuration, and and one one, you can say, condition is saying bare minimum I need to have one executor, one, you can say, core for an executor. So that is one condition. So over here, I need to decide like how many executors are possible within this particular cluster. So there are certain rules, and based upon those particular rules, we guys are going to decide like how many executors are possible. Okay, and for that particular stuff, we are having two approaches or two rules basically, you can say. Huh? Approach one, approach to have, say, approaches to have, so approaches for, say, executor calculation, huh? Okay, so there are two approaches, huh? One is thin executor and second one is fat executor. Okay, so these are two approaches in order to do the calculation for the given cluster configuration or given cluster capacity. and that like how many executors are possible. So thin executor and for fat executor, these are two approaches. So thin executor is saying, say I need to have, I am going to provide bare minimum capacity. I in this we are going to provide least capacity for minimum capacity, to each, you can say, executor. What we have seen, an executor is nothing but the combination of uh, but combination of memory and core. So the thin executor approach is saying, say we are going to provide the minimum capacity to each executor. Minimum capacity will be there, and minimum, what is the bare minimum capacity for core in each and every executor? That is, say an executor must have at least one core. Okay, that is the condition, like at least we need to have one core in an executor. Okay, so if I'm saying that I'm going through with thin executor approach and I'm having this particular configuration or capacity, cluster capacity, this is the cluster capacity. So you need to tell me how many executors are possible in this particular cluster. I'm having, say, five node cluster. You just need to do the calculation, huh? Five node cluster, and each machine configuration is this one, huh? Each machine config, each machine config. Okay, so this is the configuration for each and every machine. Okay, so you need to tell me how many executors are possible from this particular capacity. How many executors are possible? We are having 80 core. We are having 80 core. So how many executors are possible?
80, sir.
80.
80 executors, huh? Because like each executor will have one core. So 80 executors will can approach 80 executors, 80 executors with capacity or with config, basically one core. Now you need to decide the memory as well, huh? So one core is there, and uh, 80 divided by 320, huh? So 4 GB RAM, huh? Right? Is it fine? Is
Yes,
it
sir.
fine? Okay, perfect, huh? So I will be having one core plus 4 GB RAM in each executor, and inside the cluster I will be having 80 executor. What but what about a machine? In a machine, in a particular machine, how many executors are there?
4.
Machine, you are having 16 core in each machine. So how many executors are possible? How many executors are there in a
5, sir.
machine? Why 5? You are having 16 core.
16 executors.
16 executor, and 16 cross 5, then you will be having 80 executor. Now in cluster, we are having 5 node cluster. Each machine configuration is 16 core. So in a particular machine, we will have 16 executor with capacity same 1 core and 4 GB RAM. Clear? Is it fine?
Yes, sir. It's fine.
Are you able to get all of you? So this is based upon thin executor calculation, right? In 5 node cluster, which is having this particular configuration, 16 core and 64 GB RAM, and thin executor is saying, say, at least I should have one core, because like over here we will be running with minimum capacity. Okay, minimum capacity for an executor, like it must have at least one core. So if we are talking about one core, so uh, inside the cluster we were having 80 core, so 80 executors will be there with this particular capacity, one core plus 4 GB RAM in each executor. Now you can try to think onto this particular diagram. Say once this particular resource manager is initiating an application master, and application master is going to bargain resources, then it is going to provide, say you are having 5 executor in this node manager, 10 executor in this node manager. It might be possible, say certain another applications are going on, and you need to have the resources or remaining resources. You will get the remaining resources only. It is not like that, say some applications are occupying certain resources and you will be given those particular resources. No, it will not be possible. It is not, it is going to see like this much of resources are available in my cluster, and I'm going to provide these particular resources. Might be possible, say the application master is asking say 10, and the yarn manager, the resource manager, is going to provide 5 based upon this particular availability of resources inside the cluster. Another thing, say if all the resources are occupied and still we are having certain applications that are coming, then certain queuing mechanism is there, like the new applications will be queued, and that will be like first in first out basis. Certain algorithms are working, like if an application is coming, then it will be queued, and in a queue, uh, the application which is coming first, that will be moved out first for the execution. That particular application will get the resources. So try to think in that particular way, like say it is not limited to say providing resources, but what will happen, like once the cluster is not having enough resources, what will happen once uh, like all the resources are occupied, and what will happen, say if certain nodes are, you can say, not available or down due to any issue. So over here this resource manager is going to, you can say, do that particular stuff, huh? Like the driver is also running over there, that is like going to get the feedback from this particular application master and all. So all of these particular things are linked together in order to provide you the good functionality with respect to a particular job, huh? So that is, let me come back onto the point, thin executor. So we are running with minimum capacity over here, and based upon the minimum capacity, we guys are going to divide the total configurations and provide the resources uh, to an executor. So that is thin executor approach. Now the second stuff is fat executor, huh? Fat executor. So over here we are having focus to provide maximum resources to an application, okay, to an executor. So focus to provide max resources to an executor. So over here maximum resources are provided to an executor. So say we were having this particular cluster, 5 node cluster, and this is the configuration. Now just try to think based upon the machine configuration. Okay, say 5 node and with this particular configuration, it is not like say we will be having say 80 executor. Say we will be having this particular capacity. Cluster capacity is this one. This is the cluster capacity. 5 node cluster, and 5 node cluster. Inside the 5 node cluster, this is the configuration for each machine. Okay, and the cluster capacity is this one. And if we are talking about say provide maximum resources to an executor, it is not like say 80 executors are given to a particular executor. 80 cores are given to a particular executor. So over here, we just need to think the capacity of each and every machine. Basically, say, try to focus over here, friends. Try to focus, say, machine 1, machine 2, machine 3, and machine 4, machine 5. Okay. So say these are the machines what we are having, or you can say worker node. Say worker 1, worker 2, worker 3, worker 4, and worker 5. These are nothing but say worker node. Let me mention over here. Say worker node, worker nodes. Inside the Spark, what we are having worker nodes. So these are like the worker nodes with this particular configuration. Say machine 1, machine 2, machine 3, machine 4, and machine 5. So this is the configuration of each and every machine. Now, cumulatively, like the cluster capacity is this one, but what is there with respect to these particular executor? It is not like say, just a minute, let me do a little bit spacing for better visibility and understanding. Okay, so say it is not like say the 80 cores will be given to one executor. If one executor is given 80 core, then like how the movement of record. So these are physically you can say uh, different machines. So this particular machine 16 core, these are the boxes basically. This is one box, this is another box, this is third box, this is fourth box, and this is fifth box. Now if what we are going to like provide in an application, we are saying say executor one with this much of core. Just try to think like say we have given the 80 cores to an executor. Okay, so 80 cores, these are 5 machines. So how the execution will happen? What are the things that will be given to like machine 1? What are the things that will be given to machine 2? What are the things that will be given to machine 3, 4, and 5? So we can have executors from these particular machines. Okay, it is not like say we are going to club these particular resources in one executor and provide the provide to an application. That will not make any sense. Okay, because these are the physically you can say different machines. This particular box is another machine, so we need to do the calculation based upon these particular machines only. However, what is possible, like for 16 core, all 16 cores which are available in in a particular machine, those particular cores can be given to say one executor. Say executor 1 executor 1, executor 2, executor 2, executor 3, okay, executor 4 and executor 5. Okay, what I want to say over here, executor 5. Okay, so based upon the cluster configuration, we are going to like provide the number of executors, but it is not like say cumulatively I can give all the resources to an executor. Like all the cluster resources can't be given to an executor, but a machine capacity, you can say a node capacity is given to a particular executor. Okay, however there are certain another you can say things as well, like some things, say if a machine is having 16 core, then one core we need to avoid, we need to avoid for say operating system. Okay, one core we need to give say yarn and all. So those particular things we will you can say learn later. But you can what is the thing that is, what is the main point over here, like if we are going to like do the calculation based upon the fat approach, it is not like say all the cluster configuration or capacity is given to one executor, but we can give a node capacity to an executor. A node like a machine capacity is given to an executor. So machine 1 is having 16 core and 64 GB. So this particular configuration, this particular node configuration or machine, you can say capacity, is given to this particular executor. So what I can say in this particular case, in this particular cluster, I can have 5 executor and with the node capacity. Node capacity is this one, 5 executor with 16 core CPU and 64 GB RAM each. So this is the you can say cluster configuration. This is the cluster configuration, and from this particular cluster configuration, I can have this much of executors. Just have a look and ask if you are having any doubt. Just have a look onto this particular stuff. Just have a look. So what do you understand with this particular calculation? Rohit, Shivam, Vandana, Rahul, Swati, what did you get with this particular fat execution cluster calculation, capacity calculation? Anyone?
That we cannot combine like two different machines to increase the like processing capability of executor, but
Hmm.
one full machine can be assigned to one executor. So
That is fine. Now, another stuff. So that is fine. Like 80 executor and 80 core, and you can say 320 GB of the RAM. And each machine say is having 16 core. So if I'm talking about say, if I'm saying say 3 executors to each machine, 3 you can say core 3 core to each executor. I'm giving 3 core to each executor. So how many executors are possible in a particular machine?
5.
5 executor. That is fine. Nah? And say 3, 5. Okay. Okay. So you just need to like do the calculation based upon the machine configuration, right? So this is nothing but say fat executor, huh? And like machine one can have one executor, like from one machine, first machine we can have first executor, second executor from second machine, and fifth executor from the fifth machine. So in this particular case, what we are having 5 nodes in each. We were having 5 node cluster. This was the cluster configuration. Okay, and from this particular cluster configuration we can have 5 executor, and the motto is to provide maximum resources to an executor. This is the, you can say, approach with respect to fat executor, huh? Now we have seen thin executor, like that is working on to the minimum capacity, and we are having fat executor that is working on to the maximum resources, huh? Like to provide max resources to an executor. So thin executor and fat executor we have seen, but which one is better? Which one is providing us a good outcome? What do you think? Which one is better? Are we Do we need to move with fat executor approach, or we need to move with thin executor approach? Basically the motto is to provide enough resources to an application. Okay, and enough resources in terms of, you can say, core and memory. Resources are nothing but core and memory. Okay, so what do you think, which approach is good out of thin and fat executor approach? Out of thin and fat approach, huh? Which one is good? Which one we need to prefer? Any idea? Any guess? Do a blind guess with certain, you can say, inputs. What, like why you are saying say thin executor approach is good or fat executor approach is good, huh? Which approach is good? What do you think, like thin approach is good or fat approach is good? You just like think what like we have learned so far, certain optimization techniques, huh? With respect to certain optimization technique, like those particular things uh, can create impact over here in deciding like thin approach and fat approach. Which one should be good?
So fat approach will be good. Like if we go with a thin approach, it will be having more partitioning and everything. So that will basically increase your latency in
No, no,
your
no, 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 no,
work.
no, 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 no. You are mixing two things. Huh? Partition, partitions are given to executor. It is not like say based upon executor we are performing the partitioning. Partitioning is another stuff, and partitions are given to executor. And just try to think in this particular way. Say I'm having 5 core in each say over here, like how the parallelism is happening in this particular, you can say, spark, huh? Say machine 1, say machine 1, machine 2. Just pay attention over here, huh? Machine 2, machine 3, machine 4, machine 5. So the first level of parallelism is, say, the task that we are having that is divided among these particular machines, huh? Okay, that is divided to these particular machines. Then these particular machines are having executors, huh? Say executors, like multiple executors are there over here. Say if we are having thin approach, huh? Or like say we are having say 5 executor or 10 executor, 10 executor in each machine. So based upon like we can have multiple executors over here, huh? So that is fine, nah? So first level, like the task is divided among among machines, and the machines are having executors, and executors are having then core, huh? Okay, and cores, like say if 16 cores are there, just like think with this particular case a 16 core, huh? Now in parallel 16 you can say partitions will be given to these particular cores, huh? So or you can say in at a particular time this particular executor can work onto 16 partitions, and say over here like in this particular machines, like we are having say 5 machines, and 16 partitions are given to each and every, like we are having say 5 executors. So in total, like we will be having say 16 cross 5, 80 tasks. Okay, so parallelly 80 onto 80 partitions the execution will be, you can say, will be performed, huh? So just try to think in that way, like how parallelism is working in Spark case. Partitions are given to you can say machines, then machines are having cores, executors are having cores, and cores are, you can say, multiple in nature, like say if I'm having 3 cores, so in that particular executor it can handle 3 partition in parallel. Okay, so in this particular way the parallelism is working. So partitions are decided first, and it is not like say I'm having this much of core and I need to have this much of partitions, huh? So that is the stuff, huh? Partition is pre-decided, huh? Okay, another point. Okay, so let me explain it for you. So both of these approach are not good, huh? Neither like thin approach nor the fat approach. Both of these approaches are not good. So why like thin approach is not good? Because like if we are having thin approach, then we will be having, you can say, a lot of executors. And try to like recall the broadcasting, what is happening in broadcasting. We are broadcasting the small file to onto the executor. If like we are having 80 executor, so 80 copies of that particular file will be, you can say, will be 80 replication of that particular file will be there, or 80 copies of that particular file will be there inside this particular cluster. So that will create an issue, and we will be having certain, you can say, input and output time. Like if we need to move 80 uh, copies of that particular file to all the executors. So because of that, like thin approach is not good, issue in broadcasting, like multiple copies during broadcasting, multiple copies of small files inside the cluster. Okay, so that is the issue in thin executor approach, over here fat executor, so with respect to fat executor, uh, the main agenda over here is to provide maximum resources to an application, to an executor. So it is being identified in a research, like if you are providing, if you are providing more than 5 executor, sorry, more than 5 core, to an executor, then the the throughput of uh, SDFS is will suffer. Okay, or you can think in this particular way, like if you are providing the more than 5 core to an executor, then the outcome will not be good, will not be good. Like say, what is our assumption, like if we are increasing the resources, then the performance should increase in that particular way. Like say, if I was having two executor and uh, I was having say 2 core in an executor, and if I'm going to like double 2 to 4, so 2 to 4 core in an executor, then my expectation is like I will be having uh, you can say double performance, or you can say the latency must be you can say half. Like say previously, if I was able to do the execution in 1 minute, so it must be executed in 30 seconds. So my expectation is like if I'm doubling the resources, the performance should be doubled. But it is not like the case. Once I'm having more than 5 core with an executor. So the performance is not increased as the you can say percentage increase inside the resources. So at that moment the throughput is suffering. So because of that particular reason as well, like the fat approach is not good. Now once we are having second point with respect to fat executor approach, first is like the throughput is suffering. Second one is second issue second issue is like over here I'm going to provide maximum cores to an executor, and if like maximum cores are given, then the memory will be given to an executor, and that will be maximum. That will be, you can say, based upon that particular node configuration. Now in this particular case, what will happen, the garbage collection will be taking too much time. Issue with garbage collection. Issue with garbage collection. So what is garbage collection? Basically, garbage collection, say if I am performing some task, and based upon the performance, like certain objects will be created, and if those particular objects are not utilized, those particular objects will be collected as garbage in memory. So what I need to do, I need to remove those particular objects from the memory, and that is nothing but the like clearing the garbage, you can say memory. Clearing the garbage. So it is similar to like say clearing a ground. Like if you are having 4 GB ground or 4 GB area, so that will take less time. And if like inside one executor you are having say 128 GB or 64 GB of the memory, then definitely that particular garbage collection will take too much time over there. It is similar like you can say clearing a field or clearing a ground. Small ground will take less time. Clearing the big ground or big field will take more time. So garbage collection is the another issue once we are dealing with fat executor. So both thin and fat, both approaches are not good. What we are having certain customized approach. Customized approach. So with respect to customized approach, what we have seen, like if we are having more than 5, then the performance was impacted. So what we need to do, like we need to have like more or less say 5 core with for an executor. And say if I'm having 5 core in an executor, so probably how many executors are possible in cluster? How many executors are possible? 5 core in each executor, say.
3
So 3 executors
multiplied by
in each
5,
machine.
15.
3 executor in each machine. What will be the memory? Each machine, and 15 in total in entire cluster.
21 GB MB. What is the
What is the total memory of your machine? One node.
64?
So 64 divided by 3.
21 point something.
Okay, so almost 21. So say 5 core and plus 21 GB of RAM in each machine, in each executor. Each executor. Okay. So 5 core plus 21 GB of RAM. So this is the customized approach that we need to take care, that we need to like consider for the for the for the for the executors. Now how to like define these particular parameters. So once we are going to create the Spark session, over there we need to define certain properties. Say Spark dot executor dot core and Spark dot executor dot memory and Spark dot executor dot instance, and say how many instance. Say with this particular configuration, say I'm having how many resource instances? Say 15, right? 15 executors in total, and the memory what it will be, 21 GB in each, you can say node, in each executor, and the core is say 5 core in each machine. So these are the, you can say, configuration that I need to set while creating the Spark session. Just have a look how we can do it. Executor instances, and like dot config dot config dot config dot config. So that is the proper, these are the properties, and let me copy and paste inside the creation of this particular session. And over here I can copy and paste. Okay, so this is the way like how we can set this particular configuration while creating the Spark session. So that's it for this particular session. Today I'm having certain other dependencies. Let me stop recording.